Today we'll be introducing our senior design project for Group 3. Skin Lumina is a portable multispectral imaging system designed to make dermatology more inclusive and accessible across all skin types. My name is Tatiana Catrone, and I am Skin Lumina's project team lead and an optics and photonics engineer.
My name is Ryan Rodriguez, and I'm an optics and photonics engineer.
My name is Abdullah Al-Garbali, and I'm an electrical engineer.
My name is Tiffany Tani, and I'm a computer engineer.
The motivation of this project is about creating a multispectral skin imaging device that adapts to every skin tone, with the goal of making dermatology more inclusive and improving early detection of conditions like skin cancer. It addresses the problem that many dermatology tools work well on only certain skin types, making it harder to detect conditions accurately for everyone. The background for Skin Lumina starts by using multispectral imaging and targeting the therapeutic window to achieve deeper, non-invasive skin scanning. This approach accounts for variations in skin pigmentation and structure, allowing for more accurate detection of subsurface abnormalities. The basic goal is to build a multi-wavelength imaging system that detects skin abnormalities and uses a two-scan process for more inclusive results. We are currently working on making it portable for dermatology clinics, integrating subsurface techniques like cross-polarization and designing the system to be modular for easy swapping of lenses, apertures, and filters.
Basic objectives for our project include constructing an optical system using lenses, mirrors, LEDs, and filters to minimize chromatic and spherical aberrations, as well as increasing image quality. The second one being to enable adaptive imaging with a two-scan approach for skin tone inclusive results. This includes creating an initial scan with white LEDs to gain a personalized baseline profile by adjusting the brightness of the LEDs accordingly. And the second step being to create a second multi-wavelength scan to create different images and highlight different features on the skin by iterating through a series of visible and near-infrared filters. Our advanced objectives include developing a scalable and portable structure for real-world usability, and to use cross-polarization and optical enhancements for at least 1024 by 1024 pixel images. And lastly, our stretch objectives include exploring modular add-ons, enabling customizations such as interchangeable lenses, filters, and optical elements, as well as a mobile platform to support future use cases. We'll now be explaining the key part of our project, the optical design. So as you can see from the diagram on the left, we're going to have two clusters of LEDs consisting of wavelengths of 470 nanometers, 530 nanometers, 630 nanometers, 850 and 940 nanometers. And these wavelengths are going to be shined onto a sample, that being the skin, and that light's going to be reflected off the skin and through our optical stack. The optical stack contains two achromatic doublets in an infinity corrected system. We're using achromatic doublets to reduce chromatic and spherical aberrations. And the light's then going to be going through a stepper motor with a series of filters that will iterate through the wavelengths I previously mentioned. And then it's going to go through a aperture, which allows us to change depth of field. And then we're lastly going to have an adjustable polarizer that allows the user to change the polarization of the light in order to get better knowledge on reduce surface reflections and allow us to image what we're actually trying to image. And then lastly, it goes into a CMOS camera, which in our case is a Sony IMX219, and then this is connected to the MCU, which is how we do our data and image analysis. Some specifications. The three demoable system specifications can be seen from the highlighted ones shown below. The first being image processing time. We're targeting a processing time under 5 seconds per image, and we're going to have about 5 images. And the second one is the spatial image resolution. We're targeting roughly 10 micrometers per pixel. And lastly, we're trying to keep the filter switching time to under 1 second. Some other notable system specifications are our field of view being 10 by 10 millimeters. The system power, we're targeting between 5 and 12 volts. And we want to make sure the system is portable. And per the FDA regulations for handheld medical devices, we need to make sure that the power per LED is under 10 milliwatts per centimeter squared. On with the optical design, I'm going to be walking you through calculating the lens system parameters for skin lumina. So we are trying to make an infinity corrected system using two achromatic doublet lenses. An infinity corrected system means that we're using an objective lens and a tube lens, where the sum of the two focal lengths is equal to the distance between the two lenses. So to start the calculations, I first calculated the magnification using the sensor diagonal over the object diagonal. I found these values using the Edmund Optics website and the Sony IMX sensor website, and this gave me a proposed magnification of 0.33. This is the lowest magnification we can have to be able to image in our field of view the features of the skin that we're targeting. So now, in order to calculate the focal lengths, we had to choose an appropriate lens focal length for the objective lens based on the portability constraints and design criteria of our system. So with that in mind, I chose a 6.25 millimeter focal length lens, and then I used this to calculate the focal length of the tube lens by multiplying that focal length, 6.25 millimeters, times the magnification. This gave me a focal length of 2 millimeters. However, due to the commercially unavailableness and expensiveness of these products, we decided to go with a 5 millimeter focal length for the tube lens, which gives us an effective magnification of 0.8.
Slide, we're going to be going into how we calculated irradiance and spot diameter for the system. The optical power values for our LEDs come directly from the Thorlabs datasheets. Using their maximum output at 50 milliamps, we calculated the corresponding irradiance. We then determined the expected spot size by hand before ordering lenses and then verifying these results in Zmax as seen on the spot diagram on the right. This is to ensure proper focusing onto the camera sensor.
Next, we are going to be calculating the spatial resolution of our system, which is the ability of our system to be able to record fine details and features that we are targeting. We calculated this by taking the field of view dimension, which we wanted to be 10 millimeters in both the horizontal and vertical directions, divided by the number of pixels in their respective directions for our camera sensor. And this gave us a camera imaging spatial resolution of between 3 and 4 micrometers per pixel in both the horizontal and vertical directions.
These calculations show the theoretical penetration depth of some of our chosen wavelengths based on their scattering and absorption properties. As the 3D diagram illustrates, shorter wavelengths penetrate less deeply, while longer and near-infrared wavelengths reach deeper layers, which directly impacts the imaging feedback we obtain.
As far as imaging technology and camera selection goes, we considered 3 different imaging technologies: CMOS imaging, CCD imaging, and using smartphones as leverage for imaging. And some of the pros to some of these is CMOS is lower power, more cost effective, whereas CCD is way better performance but more power hungry. And smartphone also offers us a more user friendly and higher image processing than the other two. But ultimately, we ended up choosing CMOS for its cost effectiveness and lower power requirements. As far as the actual camera selection goes, we ended up choosing the Sony IMX 219 sensor module, and we chose this module mainly to allow us to meet our 2 megapixel resolution target, as well as it being IR sensitive, which is key for our skin lumina multispectral approach, and it is very cost effective.
Lumina's illumination source, we use multiple LEDs in a multispectral system. Using individual wavelength LEDs in a multispectral system enables precise control of clinically relevant wavelengths for skin imaging, providing targeted issue contrast while remaining simpler, smaller, and less expensive than hyperspectral imaging. Optical filter selection, we correlate them with our chosen LEDs using visible narrowband filters chosen to isolate each individual LED wavelengths. The chart on the bottom left shows the transmission spectrum of our 470 nanometer filter, where you can clearly see the narrow bandpass region that only lets the target wavelength through. The chart on the bottom right, in red, shows the optical density across a wide wavelength range, which illustrates how effectively the filter blocks unwanted light, within higher optical density values meaning less light leakage outside of the passband. Slide lists factors in our lens selection that we took into consideration when choosing 2 achromatic doublets for the system. In the colorful Zmax ray diagram, the objective plane is shown on the left, where the light from the LEDs will reflect off of the sample skin before passing through the two chosen lenses to the imaging plane shown on the far right of this system.
The system is powered by a battery pack with a battery management system that feeds into a buck converter to create a stable supply voltage. This regulated voltage powers the Raspberry Pi, microcontroller unit board, and other peripheral devices. The Raspberry Pi controls the imaging sequence process and serves as master to command the MCU, which in turn controls the motor and LED driver. All components share a common central ground at the voltage regulator, essential for establishing stable potential throughout the entire circuit. Lumina device is powered by 4 battery cells in series of lithium iron phosphate. This gives a voltage of approximately 12 volts, which is used to power the entire device. A battery was chosen for its chemistry of long-lasting cycle of life and good thermal stability compared to the other lithium-ion batteries. A battery management system gives the device portability and the ability to be charged and used wherever. It is also key for safety monitoring the voltage and current of the cells to protect from overcharging, overdischarging, and short circuits. M2678 integrated circuit chip is powered from the battery along with extended circuitry of RLC components. The LM chip is the heart of the 12-volt to 5-volt buck converter and is well suited for its role as a regulator, as its efficiencies can reach up to 92% while offering efficient load regulation, keeping the output stable regardless of any input changes. The 5 volts at the output are more than sufficient to supply the rest of the peripherals that feed from this node. The Raspberry Pi is powered by the 5-volt regulator, but operates on 3.3 volts through its own internal proprietary voltage regulation. The Pi board handles the imaging sequence process through organized commands to the MCU board and to the camera used to capture and process the images. The Pi board is configured as the master board and gives command to the MCU board of what instructions to execute and in what order. The different operating voltages of the MCU and Pi board make instruction given from the Raspberry Pi distorted and untransmittable. Both boards are connected at their own TX and RX pins, so a logic level shifter is used to act as an intermediary device to regulate both board voltages for clear communication. Because the MCU board operates at 5 volts and the Raspberry Pi operates on 3.3 volts, a pair of resistors in a voltage divider configuration serves as a logic level shifter. The MCU board is powered by the ATM Mega 328P-PU chip. This board configuration acts and replicates the Arduino software, which is used to send commands to the peripheral parts connected. The board directs the dermal scanning process by holding and issuing all of the necessary routine commands. There are 6 pulse width modulations on the board. These are special due to their capability of adjusting the amount of power being outputted for precise level control. The standard digital input-output pins offer no modulation of its output level and offer only a high-low output used for less complex hardware. D channels are regulated by the MCU board and is separately powered by the 5-volt buck converter. 6 groups of parallel resistors for each channel wire were calculated using the LED's forward voltage value and its active amperage draw. 6 pulse width modulation pins control 6 LED channels. These pulse width modulation pins are connected to 6 N-channel MOSFET transistors used as LED drivers to provide protection and offer precise control of LED aspects such as brightness and dimming. The motor is what rotates the filter wheel containing different wavelength filters. The motor driver is the intermediary point between the MCU board and the stepper motor and is powered by 2 separate pins connected at ground and the 12-volt node. The driver executes instruction through 4 additional pins that connect to the digital input-output pins on the MCU board.
I'm going to walk you guys through how our software design looks. So first, the Raspberry Pi camera module will take an initial image under the standard white LED illumination. This image is then processed using a combination of OpenCV techniques to detect potential skin abnormalities, such as moles or scars. The image is then converted to grayscale, which simplifies the process of edge detection and contour analysis for finding boundaries. And then blob detection is applied to confirm the presence and approximate size of any detected regions of interest. The results for potential skin abnormalities will be logged, and then we will move on to skin color and texture classification. The software will analyze a central patch of pixels, convert them to hexadecimal code, and then classify the skin color into a series of categories, such as fair, medium, or dark. Depending on the classification, this will determine the LED's brightnesses, and the Pi will communicate to the Arduino the parameters for the LED intensity. Once the LEDs are set, the Pi will instruct the Arduino to cycle through the filter wheel, capturing images through each filter. Once these scans are complete, the Pi will upload the image and its metadata to the MERN backend. Speaking of MERN, let's dive into our full stack website. So we will be using a MERN stack, but I did evaluate a serverless Jamstack that used fast API, Supabase storage, and Netlify. I initially had liked this because it was low server maintenance, but it required more coordination between services and was a bit more of a learning curve. As for the LAMP stack, it just isn't as modern or easily scalable for our use cases. In particular, the real-time streaming tasks we require, such as showing upload progress and handling initial image scans, are much easier to implement in Node.js, which serves as the backend for our MERN stack. Node.js's event-driven model is better suited for continuous updates, whereas LAMPstack's traditional request response approach makes real-time features more difficult to implement. With MERN, we get a clean and scalable upload pipeline. Node.js with Express will handle our backend. For our data layer, we'll be using MongoDB Atlas to store flexible metadata about each scan. The actual image files will be stored in S3 or Cloudflare R2, which are built to handle large media files. On the front end, we will be using React, which allows us to create an interactive interface where users can easily view and interact with their scan results. The combination of these technologies not only match our team's experience, but also ensures our system can scale as we add more images, more users, and more features.
Let's dive into some design constraints for our project. First, economically, we would like to stay within a budget of $500 to $750, utilizing off-the-shelf components along with 3D printing and laser cutting to keep costs manageable and the system affordable. For time, we would like the project is limited by 2 semesters, so both workload and design have been structured to align with this timeline. For environmental, the system operates on low power with battery support, avoids disposable parts, and is designed to be energy efficient and environmentally conscious. For social and ethical, the project addresses a critical health equity gap by providing inclusive skin analysis across all skin tones. As a non-invasive device, it avoids the regulatory burden of high-risk FDA classifications. For health and safety, we would like to remain non-invasive. Our LED power levels are limited to under 10 milliwatts per centimeter squared, and the system uses low voltages with no exposed mechanical parts to ensure user safety. For manufacturability, we are relying on commercially available components. This will make the system inherently scalable and reproducible, supporting long-term manufacturability. And lastly, for sustainability risk, the system is designed to be modular, allowing customization of lenses, apertures, and filters. It also leaves open pathways for integration with AI-based analysis in future software development. And the device is classified as low risk to its conservative design, skin-safe operation, and thorough testing protocols. All human trials will undergo IRB review to ensure compliance and uphold ethical standards. Key standards for our system include IEC safety standards for laser products. This is basically ensuring that the LED system does not pose ocular hazards and confirms the power levels are safe. Some medical electronic equipment standards guarantees safety and electrical design, especially for skin contact or handheld usage. There's also skin color measurement standards for skin reflectance and colorimetry, which is used for calibrating imaging across diverse skin tones. There's also biomedical engineering standards, ANSI standards for imaging devices, and optical device standards, all of which have been applied and followed throughout the process of designing our system. Key safety requirements of our system include LED exposure safety, ensuring that all LEDs operate under safe power thresholds, as mentioned previously, the 10 milliwatts per centimeter squared, and device follows the IEC standard set by the country. Thermal control, we're focusing on insulation and ventilation to ensure in the enclosure to ensure proper thermal regulation for electrical system. Electrical safety powered by low voltage between 3 to 12 volts, regulated battery systems, which is reducing electrical shock. Mechanical safety, we're designing our system with no exposed mechanical parts to ensure safety. We're going to try to keep in mind an ergonomic design to build a lightweight handheld device that will reduce user strain while operating. And lastly, we're going to be clear and concise in our user instructions and data handling for security protocols. Prototyping and testing goes. Currently, we are working on prototyping the optical stack or the lens system and all the components to go with this. This includes the camera mount, polarizer, lens mounts, filter wheel, and many other parts. And some of them are shown to the right. We have our filter wheel, polarizer setup, and a lens mount that we have designed. We are using Onshape to CAD model most of the parts as we are trying to make the prototype portable and modular. And as we are looking forward to the future, we plan to then start implementing our pulse width modulation LED system with this optical stack to begin testing and collecting image data for the software side of our system. This table shows the distribution of work and who's responsible for what within our project. To note some of them, Tatiana is responsible for the visible imaging systems, while I'm responsible for the near infrared imaging systems. Tatiana is responsible for the LED and filters. I'm responsible for the camera and optical stack. And then Abdul is responsible for anything hardware and electrical, while Tiffany is our designated software person. And lastly, to wrap things up, this shows our current bill of materials as of September 12th, 2025, including all of our optical components, electrical components, PCB, and even included a shipping estimate. And this total came out to $1,114.87. Thank you again for tuning in to our presentation on Skin Lumina, an inclusive multispectral skin analysis device. Please feel free to reach out with any questions. Thank you.